Hey, pre-calculus, we are looking at section 12.6. We are going to start the idea of the binomial theorem by talking about Pascal's triangle. Let's take a look. Pascal's triangle is a triangle that is credited for Blaise Pascal, a mathematician like back in, I think, the 17th century. But there's evidence that this concept, though we credit Pascal with it, was discussed and used way back in the 11th century by Chinese mathematicians. And if you're interested, you can look up some more information about that. And so the way this triangle, you see it looks kind of like a Christmas tree. It's like a Christmas tree of numbers. The way this triangle of numbers is put together is that there's going to be ones all along the outside. Each row will continue to have a one more number. So we start off with 1, 1, and the way we fill out the inside of the triangle is by adding the two numbers above that are on the left and right of the number. So for instance, where did this 3 come from? It came from 1 plus 2 and 2 plus 1. Where did this 10 come from? 4 and 6. You guys get the idea. 4 and 1 gave me the 5. And so what's the point of this? What is beautiful about Pascal's triangle? Well, first of all, what's kind of neat about Pascal's triangle is the fact that there's some real just interesting little things that come up. So we saw how we built it. I went and, took the liberty of getting a better copy of it. And so one thing is, if you were like to highlight a couple of things, right? A diagonal, if you wanted to add those up, 1 plus 2 plus 3 plus 4 plus 5, well, that's 15. And that can happen all along the path. Let's say if I did this. So you can try it if you don't believe me. You can add up all of these numbers and you'll get 1,287. Let's say that's not that interesting to you, which is fine. Okay. You also will see that right here, you've got counting numbers in a diagonal, right? That's pretty cool. Maybe that's not that interesting. But if you were to take the time to color in the odd numbers, let's say, you get this wonderfully fractally pattern that's going to result in these cool triangles that are of increasing size. It looks more interesting when you look at a bigger one. But there's just really all these little cute little treasures. But the way that we use Pascal's triangle for binomial expansion, which is what we're going to talk about now. So if we look at Pascal's triangle with the idea that this first row is row 0, row 2, row 1, row 2, so forth and so on, what we see is something pretty cool. If I take a binomial, and that's a two-termed expression, so a plus b to the 0 power, I get 1. Anything to the 0 power is 1. If I then take a plus b and raise it to the first power, I just get a plus b. I get 1a plus 1b. If I take a plus b, that quantity, that expression, and raise it to the second power, if I take a little bit of time and FOIL it out, I get 1a squared plus 2ab plus 1b squared. I'm hoping that you're seeing it. If I take a plus b and raise it to the third power, I'm looking at row 3 now, and I were to expand it, I get 1 times a to the third power plus 3 times a squared b plus 3 times ab squared plus 1b to the third power. Let's see if I can fit that there. Are you guys seeing what I'm selling? You seeing what I'm trying to show you? The relationship between Pascal's triangle and the binomial expansion is that indeed the triangle rows will give us the coefficients to a binomial expansion, and that's what we're going to use for the next example. So for this example 1a, let's go ahead and take a look at this first situation where I'm going to expand x plus y to the 6th power. What I'm going to do is find the 6th row, and I'm going to highlight that. So 4, 5, and 6, highlighting the 6th row rather sloppily. Let's try that one more time. There we go. We've highlighted that a little bit better. So what we're going to do is expand this situation by using, instead of multiplying it all out, we're going to use the binomial expansion based on Pascal's triangle. So we're using the 6th row, and here's what we're going to recognize. We're going to recognize that the first term will be x to the 6th power, where the variables in the second term will be x to the 5th power, y to the 1st. I want you to notice that the sum of the variables in each term will always be 6. So watch what's going to happen next. We're going to get x to the 4th power, y to the 2nd, x to the 3rd, y to the 3rd, x to the second, y to the fourth, x, y to the fifth, and then y to the sixth. So this would be the relationship that we're going to see before I put the coefficients on. And then now when I put the coefficients on, I've got 1 x to the 6. I'll leave the 1 out of it since there's only one of them. 6xy to times y to the first plus 15 xy to the fourth, y to x to the fourth, y to the second, plus 20. And then you see what we're doing. I'm just plugging in these coefficients like that. And so this is the expanded version of this binomial here. And we use Pascal's triangle to do so. So that's pretty neat. I think that was kind of cool. What we'll do is we'll look at doing it over here. So let me just go back and reiterate. We raised each term, each of the first term will descend in terms of power. Notice we went x to the 6 all the way down to x to the 0. And then the ascending values of y will start with y to the 0 here and then go all the way up to y to the 6. Notice that each time the exponent, the degree of each term is still going to be 6. All right, I'm moving over here to this example. Let me see if I can start it over here. So this is going to be a little bit different. First of all, we are over in the we're over on the 7th row because we're raising it to the 7th power. And so let's highlight that 7th row, a beautiful green color. So that's to keep us focused. And then the next thing we're going to do is we're going to think about, before we bring the coefficient, well, maybe I'll just bring it all together. So watch this. You remember the first term here was the first term to the 6th power? Well, we're going to do that same here. This term to the 7th power. So this will be 3x to the 7th power. Watch how I do that. I need to put a parentheses around that because that is 3 to the 7th power times x to the 7th power. You didn't know it could look like that, but it can. Okay, so next thing we're going to do, and that's going to be 1, so I don't have to put the 1 there. So that's 1 times that plus 7 times 3x to the 6th power times 2y. Next term, 21 times 3x to the 5th power plus 2y to the 2nd power. Oh, I'm sorry, times 2y to the 2nd power. Let's put that there. And I'm going to keep going. I'm going to use 35 now. 35 times 3x to the 4th power. And then I'm going to have 2y to the 3rd. And I'm going to keep going with that. Whew, okay, so there it is, all expanded out. Okay, well, not really, because I guess now we should do some multiplication. So if I were to take 3 and raise it to the 7th power, that would end up being 2,187 times x to the 7th power. Yes, I know. And then 3 to the 6th power times 7 times 2 is going to end up giving me 10,206, and that's x to the 6 y. And then if I were to, you see where this is going, right? So I take the 21 times the 3 to the 5th times the 2 to the 2nd. If I were to multiply all that together, I'm going to get 20,412 times x to the 5th, y to the 2nd. I'm going to spare you the explanation. I'm going to write it all out for you guys. So when everything's expanded out, this is what we would get. And so what I want you to see is that I guess I wouldn't say lied, but I said, hey, the Pascal's triangle is going to give us the coefficients. Well, it's going to help us get the coefficients, but it doesn't really give us the coefficients. We have to do a little bit of work, especially in situations where we're not just raising an x plus y or an x minus y to a power. By the way, if this had a minus sign in here, what you would see is that every sign would flip-flop. And so what that means is the first term would be positive, but the second one would be negative, because if the second term were negative, then 2y would be negative and it would make this whole term negative. But then if I raise that same negative 2y to a positive power, it would be positive. So that's why you would get a plus minus plus, or plus minus plus minus plus minus when you had a negative value. All right, let's go ahead and take a look at the next problem. Okay, so let's look at example 2, and just for the record, I don't really like this problem as it is presented in the text, so I'm doing it a little bit differently. Of course, you guys are free to go ahead and check out the text and see if that way makes better sense. But what I'm going to describe, I think, is going to make a little bit better sense, even though I'm introducing something new that's not in the text. All right, I know that doesn't sound very promising, but let's check out this problem. So this problem is going to refer to the beginning of the text where we talk about Bobby McKay. I believe that's how McKay, an Iowa seamstress who gave birth by cesarean section to 7 babies. The birth of the septuplets was the first of its kind in the United States back in since 1985. The babies born just after 30 weeks of pregnancy weighed 2 pounds 5 ounces to 3 pounds 4 ounces. And our question, if we go back up, is, of the 7 children born to the McKays, at least three were boys. How many of the possible groups of boys and girls have at least 3 boys? That's a crazy question, right? Hopefully you see it, and you might not see how it relates to the binomial expansion very, very well. But what I'm going to do is I'm going to talk about the binomial expansion away from Pascal's triangle, which is what the next example is going to be. And I'm going to talk about this counting principle right here. So this counting principle is sometimes it's referred to as a combination, N choose R. So if you had a situation where you had N groups of things, N number of things, and you had to choose R, this answer gives you how many ways that can be done. So if I have 7 children and I need to choose 3 boys, this would give me all the possible ways that could have happened. So we could have had the firstborn could have been a boy, then the thirdborn could have been a boy, then the lastborn could have been a boy, or a number of different ways. So that's what we're being asked to count in this situation. We're asked to count in how many different ways, and how many different possible groups of boys and girls have at least, so how many different possible situations. This is so not clearly stated that I find it frustrating with the problem. But don't worry, we're going to take care of it. So if we look at the kids in kind of in order, if we look at them from, let's say we just had 7 kids and she did, and we had to think about, where the boys would land, how many different ways we could have had 3 boys. So as I mentioned before, we could have 3 boys kind of in any position. This is one thing. But then, so we're going to consider 3 boys, but we're also going to consider at least 3 boys means that we have to consider how many different ways she could have had 3 boys or 4 boys or 5 boys or 6 boys or 7 boys. These are all the things that we need to think about, okay? So remember, N choose R is how I'm going to refer to this, or how many combinations of R can we have given N choices. And what we would do is we would calculate that value by following this. We would take N to the nth factorial over R factorial times N minus R factorial. So let me be clear. So if I wanted to figure out how many different ways you could organize 3 baby boys amongst 7 of these septuplets, I would have to take 7 factorial. Are you guys with me? And then divide that by 3 factorial, and then further divide that by 7 minus 3, which is 4 factorial. This is going to give me the answer. So if I were to deal with this, I would end up with, I'm going to cancel out the 4 factorial so that I have 7 times 6 times 5. 4 factorial is gone from the numerator and 4 factorial is gone from the denominator. So I'm left with 3 times 2 times 1. I hope that that's clear. And then now what I'm going to do is reduce this. I know I don't want to have to do this either, guys. And I'm going to show you how we're going to use Desmos to get through this. But the 2's canceled out here. So I end up with 35. So there are 35 different ways for me to organize 3 babies amongst 7 babies. Are y'all with me? So we took care of 3. Now we got to take care of 4. And then we got to take care of 5, 6, and 7 boys, the possibility of all those boys. And then what we're going to do is we're going to add those up in order to find the possible ways. Okay. So of course, Desmos is always very helpful and ever present on our mind. So let's go ahead and take a look at what Desmos can do. So where we can go, I made this really big for no good reason. Please forgive me. I was having some trouble with the computer. If you go over to functions, you will see down at the bottom number theory. Cancel. You'll see number theory down here, and you'll see N choose R, or the combinations. This is called permutation. So this is a little bit different. This means like this has to do when you're dealing with organizing them in an order, like a first, second, third, fourth place order, not just how many different ways we can do a thing. So this is the one that we want. We would choose that. And then in parentheses, we choose the N value and then the R value. So as you know, we would be dealing with this guy, right? I just want to show you that it works out. When I do that, I got 35, and then I'm going to add on 7 things, choose 4. So what if I had 7 babies, and how many different ways is to have 4 of them boys? How many different ways is to have 5 of them boys, 6 of them boys, 7 of them boys? And of course, maybe you could think about it, but how many different ways can you have 7 children and they're all boys? Well, there's obviously exactly just one way. Does that make sense? Okay, anyway, the answer is 99. And I hope that made sense. Let's see if we can apply what we learned from this problem to the next set of problems. So what we did in the last problem was use the binomial theorem, the part of it that really is the counting theorem. And that's something that we're going to talk about a little bit later, hopefully if we get the chance to before the end of the year. However, now what we're going to do is use this as the binomial theorem. So again, we're still expanding different expressions like this, but now instead of using the way that the text wrote it out, by the way, these are exactly the same. These are exactly the same thing. I just think that it might be more helpful if you looked at it like this than like this. So what we're finding is the coefficient of these expanded terms. So if you look, and that's exactly what's happening here. You notice we have x to the nth power, and then we have x to the n minus 1, and then y. So we see that decreasing of the first term in terms of its power and increasing of the second term, and we see that process going. And then what you see is this weird expression that kind of gets big and a little bit unwieldy. What I want you to see is that that expression is just this coefficient. So why is there, like, for this first term here, notice that this term and this term is the same, and there's nothing here. There's that understood one from back in Pascal's triangle. Well, think of it this way. If I have n things and I choose none, how many ways can I do that? One time. If I have n things, I said none and not one. So if I have n things and I choose none, I can only do that in one way by choosing none. But if I have n things and I can choose one of each, well, I can do that 7 times. So I get n there. That's why the second term has n as its coefficient. If you're not loving this, feel free to turn to this and use it for your expansion. In my explanation, I find this a little bit more convenient and concise, so I'm going to use this, all right? But if you need me to translate better, let me know and we can talk about it. So, all right, guys, use the binomial theorem to expand this. So now, instead of having to pull out Pascal's triangle, I'm going to pull out this. And so I know that there's 6 terms. I know that the first term, according to what we're doing here, is going to be 1 times 2 to the x power, which is going to be 2x to the 6. And then to that, I'm going to do n, or in this case 6, right, times 2x to the 5th power times, now watch this, times a negative y. All right, so you see this sign is going to change, a negative y to the 1st power plus, and so what's that next term going to be? So here's how I'm going to do it. I'm not going to do this to get that next term. I'm going to do this. So I have n things, which is 6, choose 2. That's what I'm being asked to do. Or I'm being asked to think about 6 things, choose 2. So both of them are the same. These are equivalent statements. And so basically what I'm doing here is I'm going to do 6 factorial over 2 factorial over 6 minus 2 factorial, which is 4 factorial. Cancel out the 4 factorial, and I get 6 times 5 over 2 factorial, which is 2 times 1. Y'all with me? And then so at this point I have 30 over 2, which is 15. So I get 15 times 2x to the 4th power times negative y to the second power. So you see this term is going to be positive. And then I'm going to keep going again. Y'all with me? I hope so. I hope you're not like, what is happening? Life is hard. So if I have six things, choose 3, I could write it like this, or I could write it like this, or I could write it like that. Follow my path for a second. I get 6 factorial over 3 factorial over 6 minus 3, which is 3 factorial. I'm going to cancel out one of these 3 factorials in the denominator. So I'm left with 6 times 5 times 4. Realize that I get 3 times 2 times 1. That would be 3 factorial. So I'm getting rid of that, not writing it. And I'm only going to write one 3 factorial down here. And I'm going to write it as 3 times 2 times 1. Yeah? I'm hoping this makes sense. 3 and 2 get canceled out because that's 6, and so now we get a coefficient of 20. So I have 20 over here. Let me make this a little bit plainer, and then I'm going to stop my chatter and give you guys some time to work on it while I go work on it and give you the answer. But 2x to the third power times a negative y to the third power, which is going to give me a negative term. Let me finish filling this out for you. So this is the sort of expanded form, and when we finally expand it to finally get this form here as we deal with actually raising things to powers and multiplying, all right? So this is what we get. Let's go ahead and check out example 4. So here in example 4, we're going to be finding the 5th term of this expanded situation. And so this is why it's really nice to have this situation here, because you know, if we were using Pascal's triangle, it would be fine. We'd find that 7th row and we kind of work through it. But here we can find the 5th row by simply going to that term and finding out what it is. So the 5th term would be characterized by n over r, or n things choose 4, such that we are going to raise this first term for a to the n minus 4 power. Notice n minus 1 power, n minus 2 power, n minus 4 power, and in this case being 7, so we would raise this to the third power. And if we're raising that to the third power, then 3b would be being raised to the 4th power. So this is the, let me go ahead and change my n. This is the value that we're looking for. That was kind of easy. So now let's go ahead and calculate this. Remember, we take 7 factorial divided by 4 factorial and then divided by the difference, the factorial of the difference of those two numbers. So that's 3 factorial. Let's cancel out 4 factorial so that I have 7 times 6 times 5. 4 factorial is gone. 4 factorial is gone. I'm left with 3 factorial, which is 3 times 2 times 1. That's gone, and I'm left with 35. So 35 times the following, 4a to the third power, quantity to the third power, that is, times 3b to the 4th power. So when I take the time to multiply all that together, we get 181,440, a to the third times b to the 4th. I'm glad we didn't use Pascal's triangle for that. So we can see some really neat usages. There's some slight subtle differences. The textbook uses a summation notation form. I really like this. I would recommend this, but if you prefer the way the text kind of reviews it, that's totally fine too. All right, but for this section, that's all we got. I'm looking forward to chatting with you guys soon. Let me know if there's any questions for real about anything that we've discussed, all right? Because this was kind of a heavy topic. All right, look, take it easy. Bye-bye.